Again, my tests sometimes are, people say my tests are tough. So maybe they're a little bit tough. I guess I have to believe my students. All right, so last time we were talking about functional pointers, right? So that's the last thing we mentioned. So in this case, just going to reiterate what we did. We have a function which is defined to be average, taking to int, returning an int. Another one, different name, but the same types and number of parameters, same return type. So because functions are the same, what we can do is we can actually call a function called mystery with the two int parameters. So there's int, and then we're sending in average. But average is the name of the function. So therefore, this is not a call to the function, because once we're omitting the parentheses, that's the address of the function. So the address of the function is a pointer to a function of the same type as average. And you can see clearly that the parameter average is going, this is called the actual parameter, right? Yes?
Yes.
What's the formal parameter in mystery? What's the formal parameter? Fn. Fn. So the function pointer average is referred to by Fn. So Fn is a pointer to a function that takes two ints, returns an int. So we did this last time, and you kind of saw how that would work. All right. So in this case, calling mystery with the function pointer to average, going into Fn, Fn calls the average function of the parameters a, b, 4, and 12. But the second time, I send in a pointer to sum of squares, which is a similar function in terms of its signature, but it's a different function. So when we call Fn, we're calling in sum of squares on 4 and 12. Okay, so anybody have any questions about that? So this is called, these are called functional pointers. Of course, you cannot do pointer arithmetic with functional pointers. That wouldn't make any sense, right? Functional pointer plus 1, that would be bizarre. What does that mean? We don't know. So let's continue with this idea and see how we can extend it. And so here, I believe, I think we covered this slide as well, all right? So in this case, what we did was the type def of something called int fn. And again, if you get rid of the type def, and if you simply replace the star int fn of a single thing, it would be a header or a prototype of a function that takes two int and returns an int. But because you have the type def and you have the star, then int fn is a pointer to the type of a pointer that takes two ints and returns an int. So once I do that, then I can simplify my function mystery by saying, instead of saying blah 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 all this garbage in here, I can just say fn is an int fn. What's an int fn? It's a pointer to functions that take two int and return an int. So that simplifies things, right? So type def, even though type def looks intimidating if you're not used to it, but once you're used to it, it's not a big deal. Once you do that, then you understand that fn is just a pointer to a function. Where do type defs usually go in a program? C++. They could, but more generally, in the header, into header files. So type defs generally belong in headers. So you could put a type def in the header of some particular module. That's fine. So now, basically, same call, but now it just cleaned up this mess over here. Okay. So now what I'm going to do is I'm going to show you how we can do this type of thing in a more practical example. So notice that I have type def endfn. Can somebody tell me what is endfn? Nice and loud. Nice and loud.
Boolean type.
Boolean type? No. What is endfn? Type. It's a type def for endfn. So what is endfn? The answer always starts. It's a type, right? It's a type. So what type is endfn? It's a type of a function pointer to functions which take a void pointer and an int and return a Boolean. So if you can find a function that takes a void star and an int and returns a bool, that's exactly the type of thing that ENDFN types can point to. Remember, ENDFN is not a pointer. What is it? Give me a single word. ENDFN is not a pointer, but it is what? It's a type. It's a data type. It's a data type for pointers to functions. Okay. Now, if you look at the next method, ARBlen, notice that ARBlen, what is ARBlen returning? It says ARBlen void star ENDFN. What the parameter is a void pointer and an ENDFN, right? Okay. What does it return? Why int? Why int? It doesn't say int.
Default?
RBlen, what is it? The return type is int, but I don't see it.
You define it doesn't.
Okay, that's a question I would like you to have an answer to, but I haven't really said anything about it specifically. In C++, if a function is not given a return type, the return type is assumed to be int, which is very strange. Which is why this works. So if you don't have a return type, it's an int. Okay, so let's go to the next function. The next function, by the way, is called int end, and it takes an int star and an int returns a bool. The next one is a strn, takes a char star and an int and returns a bool. Do you notice something about these two functions? They are quite similar in type to ENDFN. They're quite similar. The only difference between them is that instead of taking a void star, they take a specific star. Guess what? A void star can accept any other type of pointer. So therefore, if the type of the pointer to function returns a void pointer, accepts a void pointer as a parameter, then it will accept any parameter. So therefore, these types can match this one. Okay, so let's take a look at the main function. So the first thing we do is we create a character array and we initialize it to this right here. A, B, C, D, E, F, G. What follows the G? Null pointer. How come? Because we constructed it as a string literal, so there's a null pointer. So A sub 0, A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, A sub 6. How many elements does A have? 6. It really has only 6 elements. It just happens that the initialization creates a string literal which allocates an extra byte, but it's really not part of the array. It's really not part of the array, so that's a kind of interesting thing. How can we determine how many elements are in the array A? I will show you this. And this is, again, something I haven't shown you, but I'm going to show you now. There is an operator in C++. There's an operator in C++. Actually, it's not an operator, but it looks like an operator sometimes, and sometimes it doesn't. So if I have the code char A bracket equals A, B, C, D, E, F, G as a string, and I have the expression size of A. Can you see it? I just wrote SIZEOF. That is, we'll call it an operator. And in a second you're going to see why it's not an operator. Size of A. Size of A is an operator that takes a parameter, can be two things. It can take a parameter of an object, or it can take a parameter which is a type. So size of A will return the number of bytes that's connected to the object A. Well, look at A. A is what? A is character array. How many elements in the array? I guess 7. You said 7. It is 7. I miscounted. He's correct. The blank doesn't count. Okay. So basically, size of A will return the value of 7. Why? Because A is an array of 7 chars. Each char is 1 byte. It'll be 7. If I had an array of 7, let's say, shorts values, it would return a value size. It would give me 14, because each short is 2 bytes. If each one was an int and I had 7 of them, that would be 7 probably times 4, 28. Size of will return the number of bytes allocated to a particular object. So if I divide size of A by size of char, sorry about that, can you see that? Size of char will return the number of bytes for a char, which is 1. So if I take size of A, which is 7, divided by size of char, which is 1, that expression will have a value of 7. Now, if A was an array of 7, let's say ints, then size of A could return 7 times 4, which is 28. Size of int would return 4, and the quotient would return 7. So we can use sometimes size of array over the size of its element to compute the number of elements it has. But we have to be careful. And the reason we have to be careful is because that only works if you're in the block that has defined that object. Once you go to a different block and you pass it as a parameter, you lose that information. And I'll show you that later on when it's appropriate.
There may be another trick.
Yeah.
If we do like address arithmetic,
Mhm.
let's say is the address of A. Okay, address of A itself. It will return the whole, like the whole address. Of the
Well, the address of,
Yeah.
hold on. So, but A is an address of
yeah,
the...
the address of the array itself.
Yes.
Okay, like let me remember. I think like if you subtract or kill the last element of this one, it will give you the actual address minus. Let me remember.
We have to talk about it. I'm not sure exactly what you're saying. I know there are some tricky things you can do, so we can talk about it.
Yeah.
But I don't want to mix anybody up right now. But for now, okay. So now we have B as an array of 1, 2, 3, 4, 5, 6 int values, okay? And that's B. That's also initialized. And then we have an integer int value called I, and then we have a void pointer called foo. What's a void pointer? It's a pointer to nothing. What good is it? You can assign other pointers that pointed something into it. Okay. Can I assign functional pointers into it? Yes. How about int pointers? Yes. How about pointers to int? Yes. How about anything that's a pointer? Yes. How about an int? Yes. Really? Yes. How about an object? Sure. Very dangerous, these void pointers. Very, very tricky things. Okay. So what I'm doing here is I'm going to say rblend. Now rblend, I'm going to bring that function back up so we can see it. Rblend is this function right here. And I'm calling it here, passing in A. A is, what type is A? Const pointer, const star. Okay, so A is going in for a void pointer. Then what I'm doing is I'm passing in strnd. What's strnd? That is an address of a function. strnd is the address of a function. It's a function that takes a char pointer and an int, returns a bool. And what I'm doing is I'm calling a reinterpret cast as an ndfn, which means I'm casting this pointer that it's pointing its functions that take a void pointer and, what is it, in an int and return a bool. Remember the reinterpret cast? That's a way to cast things. There are two things that are unrelated to each other. These are different functions. I'm allowing them to be, I'm casting it. Okay, so once I cast this functional pointer as this type of functional pointer, then this goes into rblend. So let's go into rblend. Annie is a void pointer to what? Any is a void pointer to the little a. But it's a void pointer, so we can't dereference it like that. Okay. And is end is actually a pointer to what? It's actually pointer to string end. Right? Okay. So now what's going to happen is len is equal to 0, and then while not is end any len. Now is end is really calling which one? String end. String end. So in this case, what it's doing is it's taking the pointer to the a, and it's calling the function string end. So what happens is this pointer here goes in as a char pointer, which it is. Okay? So this goes in as a char pointer. Len goes in as I, and the function returns a sub, what's the value of a sub 0 is equal to the null character. Is condition true or false? This condition is false. Therefore, len goes to 1. Okay? And so now we go back to the loop. So len is 1. Now we go and we send in the pointer again. This time, which one is the pointer? The pointer is still pointing at a. But now len is equal to 1. So now we're calling the function str, and this void pointer becomes a char pointer, and this becomes an I. Return a1 not equal to 0. Well, of course, here, true, 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 true. So 7 times it's going to get bumped. After the last bump from G, it's actually going to go on top of that null character, which is only there because we were lazy in initializing it as a string constant. If we did it as an array, we'd have to physically put the null character in there. Okay. So therefore, eventually, after we go to the G and we go to 7, this goes over here. So that's the value of len is going to be equal to actually 7, because this is 0, 1, 2, 3, 4, 5, 6. This goes to 7. And is end is going to call, again, string end, and it's going to say a7 equal to the null character. The condition will be true. Therefore, it's true, not true is false, return 7. So what we did was we counted, in a sense, the number of elements in that array. Any questions about that? So that's what arbitrary length means. In the second example, we have b as an array. And so what we're doing is we're calling arblen. This time we're passing it a pointer to int. And this pointer to int goes into a void pointer. Okay? And then this void pointer is sent into isEnd, which is now the int_end function cast as an endfn function. So it's going to be this time this function. And the condition for the end of the array is the element is equal to -1. Notice that I cleverly put a -1 here. Otherwise, I could have a real problem. So what's going to happen here, again, is I'm going to go here, and len is starting at 0, isEnd, but this time isEnd is calling the function intEnd, taking this int pointer as a void pointer, sending it to a function which is expecting an int pointer, and therefore when it's working here, notice that I'm dereferencing a void pointer which was sent into an array expecting an int pointer. So therefore I'm dereferencing the address as an int. So a sub I equal to -1, false, 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 false. That's going to happen 5 times. The 6th time is going to be true. When it's equal to true, then equal to -1 is going to be, it's going to return what? It's going to return, equal to -1 is going to return true, so therefore length will return the value of 5. Okay? That's the output. Very, very clever right there. I could have seen that. All right. Problem here. All right, so we're going to talk a little bit about multidimensional arrays and how we use them best in C++. This is called a static multidimensional array allocation. So here is the type of element, here is the object itself, or the reference, right? Or the pointer, if you will, or the array name. And this is the number of rows, this is the number of columns. So how many elements are being allocated? 6 rows by 5 columns, so it's going to be 30 elements. We can, and they are basically, okay. Now, how many rows do we have?
6.
And how many columns? Okay, but in reality, we have 1 row
30.
and 30 columns. And the reason I'm saying that is because in reality, even though we like to think as two-dimensional arrays, the storage is always one-dimensional. And so therefore, when you allocate an array 6 by 5, what C++ really does is 2 things. The first thing it does is allocate a buffer of 30 elements capable of holding 30 int values, because that's the element. And the second thing that happens at runtime by the C++ runtime system is that C++ generates at runtime what we call a mapping function. A mapping function that says that, so if you see, for example, in your code, my array sub I sub j, it has to offset from the beginning of that 30 int buffer and go to the right place. And the offsetting goes something like this. So for example, let's just say for the sake of argument that I have my array sub 2 sub 3. Sub 2 sub 3. What that means is that you're going to go to the beginning of the first element of that buffer. Okay, and I can get very fancy here on the board, although I'm going to try to control myself. What's going to happen, I'm going to go, so therefore, if I go to my array sub 0 sub 0, that's the first element. And I can cast it as a what? As an int pointer. I can cast it as an int pointer, if I wanted to. It's really an int pointer, but I can cast it as an int pointer. And then what I can do, since I'm looking at my array sub 2 sub 3, I can then add to this int pointer, remember, sub 2 sub 3, 2 times 5, which is 10, 2 sub 3, plus 3. So take the address of the first element. Actually, if I say my array sub 0, that is an int, right? So all I need to do is put an ampersand in front of it, and that becomes an int pointer. Then I'm going to add to it 2 times 5 plus 3. Does everybody understand what I'm doing? Okay, row 0, row 1, row 2. If your index is row 2, that means technically speaking, you passed all the elements in row 0 and row 1, now you're on top of row 2. But for each row 0 and 1, how many columns are there? 5. So if you are in row 2, that means you passed 5 elements in row 0 and 5 elements in row 1. If you start at the beginning of the array and you pass 5 elements and 5 elements, you are exactly at the beginning of row 2. That's why I said if you're looking for element my array sub 2 sub 3, start at the address of the very first element in that whole buffer. Then add to it 2 times 5. That's going to offset you to the linear location where the third row would begin. But so now you're at the beginning of the third row. You're at the first element of the third row. But I'm looking for 2 sub 3, which means I'm not at the beginning of the third row. I want to add 1. If I add 0, I'm at the first element of the second row. If I add 1, I'm at the second element. If I add 2, if I add 0, I'm at the first. If I add 1, I'm at the second. If I add 2, I'm at the third element. If I add 3, I'm at the fourth element. And that's what my array sub 2 sub 3 is. It's skipping 10 elements that are 5 in row 0, 5 in row 1, and then skipping positions 0, 1, 2, and going to position 3, which is the fourth element in the second row. That type of arithmetic is called a mapping function for arrays, and it's generated automatically for multi-dimensional arrays that are declared statically By statically, I mean like this. Like this. It's a static declaration. You're saying, I want an array of 30 elements, type int. But I want to be able to use bracket notation. Of course, I can also use parentheses and stars to dereference it, but that's another story. What the heck does that say? Incorrect illegal allocation. That's my magic writing over here. So notice that new ints, this is just wrong. We just can't do it that way. So we'll have to see how we do it correctly. So look at that and say bad. Okay, this is a bad one. Okay, now 4 possible ways of passing a one-dimensional array to access the element a sub I. You didn't know there was 4 possible ways, but apparently there are. So I have an array that I'm passing into a function. And so this is method X. In fact, all of these are method X's. These are not overloads. These are just examples of how you could do it. You could put into the header int a bracket int n. Or if you know there are 10 elements, you could put int a 10 int n. Or if you don't want to use array notation, you can say int pointer a int n. Or if you don't want to use a non-constant pointer, you can say int const star a int n. All of these are going to allow you to pass an array. Now, let's take a look at this one and this one. Let's contrast these two first. What do you think is the difference between the first version and the second version?
Second only takes an array of 10 elements.
You know the number of
Okay, it looks like the second one is limited only to an array of 10, but the first one is not limited at all. That's a good answer. It's not correct, though. Okay? What happens is, as soon as the compiler sees a functional definition of an array, one-dimensional array with a dimension, it says, that 10 is never looked at, ever. This is the same as this. The fact of the matter is you can pass in any number of elements of an int pointer type, or any kind of int buffer, here or here. And typically you supply the number of elements here. Now you might think to yourself, hey, I think I remember a long time ago we talked about size of A divided by size of the element type. Why do I need this? I could just say size of A divided by size of int. Aha! No, you can't. And the reason you can't is because the array is coming from a different block, okay? And it's being passed here by value, a copy. So what A is, it's a formal parameter. Size of A is 4. How about if the array has 1,000,000 elements? It's 4. Why? Because A is a constant pointer, and constant pointers have 4 bytes allocation to them. That's it. So you cannot deduce the number of elements from here. This doesn't mean anything. This compiler never uses that. It's gone. So you can put 1,000,000 here. Compiler just like, whatever. And so now we're looking over here. What's the difference here? Here A behaves like a constant pointer. Here A behaves like a variable pointer. This is the same code. The only difference here, I can say A++ here. So I can move my pointer to the second element. Here, I cannot say A++. Why? Because it's a constant. So this is most closely connected to this one. This is just bad. But you'll still see people doing it. Now, the more interesting thing, how to pass a 2D array to access the element A sub I sub j. So I'm going to have 3 values here. This one is bad. It's illegal header. Okay, we'll find out why in a second. Okay, so the first thing is, let's say I'm passing an array 8 by 5. It's possible. So therefore, this is one possible header. By the way, M and N are the row columns. Okay. So I'm passing an array 8 by 5, and here I'm passing an array and I'm saying it's 8 by 5. Here I'm just saying it's something by 5. So the question is, in this example here, we didn't have to declare anything in terms of the dimension of the array at all. But here, notice that I don't have anything that says int a bracket bracket with nothing in it. In fact, you can't do it. You can't have bracket bracket with empty brackets for a 2D array. The question is why? And the answer is mapping function. If you're going to access element a sub ij inside here, and again, let's suppose I'm accessing element a sub 2 sub 3, the mapping function says for every I value, multiply it by this number that's very important to me, because for every row 0, 1, 2, when you get to 2, you pass 0 and 1, and each row has 5 elements. So it takes the I index, multiplies it by this dimension, and then it adds the I to it. That's an integer. It takes that value and adds it to the starting address of the buffer, cast as an int pointer. And then it dereferences that element. Does that make sense? So this is absolutely, so if I ask you on a test, why is the second dimension absolutely necessary? The reason is because it's used for the mapping function. That's the reason why. So now you can say, well, what about this one? What about this one? What about this one? Well, this one is very nice, but that 8 will be ignored by the compiler. The compiler could care less about this dimension. Because why would it care about that dimension? It would only care about it if it was concerned that you're going to go too far. And C++ doesn't care if you go too far of the array. That's your problem. That's why you pass these values, these bounds that are supposed to tell you where to stay, inside the lines, right? You want to color inside the lines. So this 8 is ignored. And the 5 is necessary for the mapping function. Now, can you extend this to a 3-dimensional array? What happens in a 3-dimensional array? What do you think is necessary in the header if I had a bracket, bracket, bracket function?
Bracket could be blank, and then the second two have to have...
The last two have to have dimensions. Because a 3-dimensional array is a 2-dimensional array that's repeated over and over again. So the first dimension tells you which of the matrices you're on. So if you're on element sub 2, sub 3, sub 4, that means sub 2 means you bypassed first matrix, second matrix, you're in the third matrix, because matrix 0, matrix 1, matrix 2. So that means the 2 in the first dimension has to be multiplied by the row times the column, because the row times the column is the number in a matrix. Okay? Then you have to add it to the second index times the second dimension, which is still row column, or the third dimension rather, which is the column, and then you add to it finally the k value, ijk. Okay, now this one right here, remember, what type of parameter is actually able to go in here? A 2-dimensional array, like a 2-dimensional array like we defined a little while ago over here. We defined the 2-dimensional array like this, so therefore I can stuff this, I can say, okay, let's call this function blah, 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 and put in my array. Well, my array is basically, what type is it? It's a pointer to int, so therefore if I have that coming in, that's certainly able to come in here, right? Because that's a pointer to int. It's a constant pointer. That's a pointer to int, but so is this. So therefore this is still fine. And therefore, now, what's going to happen here is going to be a little bit different. Because notice that this header does not supply the second dimension, the column dimension. So if I say a sub I sub j, that's going to be a problem. Because how the heck is the compiler going to generate a mapping function when it doesn't know how many elements are in each column? So if you go to the third row, how many elements did I skip per column to get to this row? I don't know. You cannot use this the same way. That's a problem. But it does match. This one is just plain wrong. You can't do it. Why? Because you're saying, I want to use bracket, bracket notation, but I'm not going to tell you how to make a mapping function. Ha ha. The compiler's going to say, no, haha, on you. I'm not compiling this, unacceptable, so this is bad. Okay, so these are the mapping functions we're talking about. So basically, a mapping function a sub ij is going to be, you can take star a. What's star a? If a is if a is a array, for a two-dimensional array, then star a is a one-dimensional array, which is an in pointer. You take that in pointer, you add to it I times the number of columns plus j, and then you dereference the whole thing for the element. So if we have a sub 2 sub 3, it's going to be a, which is an in pointer pointer. By dereferencing, it becomes an in pointer plus 2 times the column, which is 2 times 5 is 10, plus 3. So it's going to be the address of an in pointer plus 13. Dereference that address, and that's how we get there. And that's how we dereference a one-dimensional array that's holding so many elements here. Okay, any questions on that? Yep.
Professor, instead of column, can we take only row in two-dimensional array, like a of 2 and just bracket?
I think so. Aladdin?
What was the question again?
Okay, so let's say you see A is basically a two-dimensional array, which is 3 by 5. So can we, if we take A sub 0, that's it, A sub 0. So that would be the first element. So can we assign that into something? Because A sub 0 should be the first element of A, which is going to be what?
Itself.
Which is going to be the first row. And I'm confusing languages here because I know you can do it in Java, and I'm trying to think whether you can do it in C++. Can you do it in C++? Can we? So for example, can I say int pointer p equals a sub 0? Int pointer p equals a sub 1. Can I do that? Go test it. Go test it and let us know. Because I don't want to give you the wrong answer. You should be able to. You should be able to. Because I'm going to say yes. I'm just going to say, and I'll tell you why I'm going to say yes. Because basically, a sub 0 would be the same thing as star a. That's it.
Yes.
The answer is yes. A sub 0 is the same thing as star a. A sub I is the same thing as a plus I star. Yeah, you can. And then I can take that and I can put a bracket. So I can say like this. I can say A plus I star bracket J. They'll take the jth element from the ith element. That's a weird combination of using brackets and pointers. But we can use all pointers or all brackets. Brackets can only be used if we have a one-dimensional array or if we have a mapping function. If we have a one-dimensional array, you can always use brackets for pointers. But if you have a 2D array, you need to have a mapping function so that it knows how far to move past the linear allocation based upon the row that's selected. All right. So essentially, A sub I sub j, this is what I was talking about here. So this is how we can access A. So A sub I sub j, this is essentially the same type of thing. So notice this method takes an array which has 5 columns. How many rows? I don't know. I'm not checking for it, but this is checking for it. This is probably checking the number of, this is probably sending the number of rows. And if we have access to A sub I sub j, that's going to be star A, and star A will be what? It will be an int pointer plus I times the number of rows plus j, dereference that int. And that's the mapping function. Okay, but the next thing I'm going to show you is very, very important because now you can probably see that we have a slight problem in passing two-dimensional arrays in C++. Specifically, if I have, oh boy. Yep, okay. So if you look at this example, let's just look at this first header here. Can somebody tell me, I'm going to ask Ronaldo because I like to hear Ronaldo speak. So Ronaldo, can you tell me what is the parameter that comes in? What's the first parameter that comes into this function? But be more yeah, you're right. But be more specific. What kind of arrays can I pass in here?
Two-dimensional array.
Yes. Keep going.
Two-dimensional integer array.
Yes. Just looking for the one more thing. Okay, neighbor of Ronaldo. Can you help him out? No? What I'm looking for the restriction on the type of array I can pass into it. It's a two-dimensional array of int. Yes? No? The restriction is that any array I pass into it must have 5 as a column number. Because the mapping function is 5. So that means if I pass in an array that's a 6 by 6, then how the heck is this mapping function going to know that? It's just getting a pointer, and the mapping function is already decided. So what we have here is we have a function called method y, which accepts any two-dimensional array as long as the number of columns is 5. So suppose I'm doing some kind of a matrix processing, all right? Some kind of matrix processing. And I need to sometimes process arrays that have a number of columns, 5, sometimes 6, sometimes 25, sometimes 1,000. In fact, I may not know at beginning of the program run how big a matrix I'm going to be processing. Which means I may not even know what this is, or I may have too many of these to define 35 different functions. I would like to have one function that takes any two-dimensional array. So I would ideally like to have this, but this is not possible. As you can see by this red, which looks black, but it's red. And the reason is because this is illegal syntax, because this is providing bracketing here without a mapping function information. So that's the significant thing. So that's why what I'm going to show you here is very, very important, because I'm going to show you how you can get around that. So what we're going to have is I'm going to show you this code right here, and then I'm going to show you how you can pass such arrays into functions. All right. So the idea is, let's take a look at the main function first of all. So the main function basically, notice that my A just means my array. Its type is double star star. So it's a pointer double, which we know is compatible with two-dimensional double arrays. So what I'm going to do is I'm going to call my function dyn2d, dynamic 2d. That will be a function rather than just statically saying I want a 3 by 5. I may be getting this information from a file or from the user, so I may not know ahead of time to hard code it into the program. So I may not have these numbers available. So therefore, this is going to create an array. Now, if I change this from 30 to 5,000, then this will return an array of 30 by 5,000 times 5,000 elements. And it will give me a two-dimensional array. The question is, what the heck kind of array is it going to be? All right, so that's a good question. So what I'm doing here is I'm calling this method dynamic 2D with a 3 and a 5. And then what I'm doing, I'm looping I'm looping for j, and I am using this array like it's a good old array. It's very cool, right? MYA sub I sub j. I mean, how the heck am I doing that? Is there a mapping function? The answer is no. There's no mapping function at all for this pointer. It's just a pointer, right? So there's no mapping function associated with it. So what I'm doing is I'm basically assigning every single element my a I sub j for every I every j. New line, and then after that I'm going to say dynamic 2D my a. This is an overloaded function, right? And what this is going to do, this is actually going to be a deallocation method. So this is my allocation method. It's called dynamic 2D. It takes two ints. This is my overloaded deallocation method, which takes a double pointer. Okay. So let's take a look at this dynamic 2D. So the first thing that happens is we have a double pointer. And the double pointer ARR stands for array, bad name. So double pointer ARR equals new double m times n. The very first thing I do, I allocate, for this case, I allocate a buffer of 15 doubles. That's what ARR is, and ARR is pointing to the first of that buffer. Okay? So I have a buffer of 15 doubles. This is my storage buffer. The next thing I'm going to do is I'm going to allocate a double star star A. So A is a pointer to double. This is just a pointer to a big buffer, big contiguous linear buffer. A is a pointer to pointer, and I'm saying give me an array of m, which is the number of rows, and I want this buffer to be a buffer of what types? Double pointers. So the array ARR is pointing to a buffer of doubles, but ARR is a pointer to double. So now I allocated another buffer underneath it, which has, in this case, with the 5, the 3 and the 5, in this case it's going to have 3 elements, and this is an array of double pointers. And then what I'm going to do is I'm going to say int I equals to 0, I less than 3. A sub I, which is, what is A sub I? A sub I is a double pointer, the first one, because it's an array of double pointers. I want A sub I, the double pointer L value, to accept the address of that buffer of 15 plus 0 times 5. Now, what's going to happen is for every value here, as j goes to 0, j less than n, j plus plus, a sub 0, 0, 1, 0, 2, 3, 4, 5, assign them all 0 values. Now I'm going to go to the second iteration, I goes to 2. Listen carefully, A2, not A2, A1 is equal to the beginning of the buffer of 15 plus 1 times 5. So our buffer ARR has 15 elements. Our buffer A has 3 elements. The first element is pointing to ARR. The next one is pointing to ARR plus 5. 1, 2, 3, 4, 5. So it's pointing where we would have the second row begin. Then I'm going to initialize all these values to 0. Then on the next iteration, when I goes to 2, A sub 2 gets assigned to ARR plus 2 times 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what I have here is I have this type of a structure. Let me see if I can show it. Oh, this is just a... That's easy. So what I have here is I have ARR, which is a pointer to, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Get the idea? So that's ARR. Then I have A, which is a pointer to a buffer, but each of these elements are double pointers. So this is a pointer to an array of double pointers. This is a double pointer, double pointer, double pointer, double, 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 double. And this is what we have here. Get it? So, after that's done, I return A. And when I return A, that A just goes into whatever I had here, which is, I forget, my A. Okay? So what happens here, so basically my A in the calling program, okay, is the same as A. So therefore it's also a pointer to double. Therefore my A is also the same as A, but A disappears. A disappears, ARR disappears. How come? How come they disappear? They're automatic, right? They're automatic. They just get created here. But how come the buffers don't disappear? Die. Dynamic. They're dynamic. They're from the heap. Okay? Now let's take a look over here. My A sub 0. What type is my A? Double pointer. What type is my A?
Might be a double pointer.
Okay, so therefore we're talking about this value, right? My A sub 0, what type is this?
Double pointer.
Okay, double pointer. So it's a double pointer. It's pointing specifically right here. So if I say, so my A sub 0 is this value right here. So if I say sub 1, then basically what that means is I'm now going to be looking at this memory location and I'm going to be dereferencing it. This is the same thing as saying my A plus 0 dereferenced plus 1 dereferenced. Same code. This is pointer, this is the reference base using star, this is using brackets. So notice that I'm using this thing just like it was, there's no mapping function. There's no mapping. I'm actually just using this as dereferencing operators using brackets. Okay? So, what do? We allocated a two-dimensional array by first allocating a linear buffer, then allocating an array of pointers to the beginnings of each row. Row 0 pointer, row 1 pointer, row 2 pointer. And this will work for any two-dimensional array. The cool thing about it now, suppose I wanted to pass this two-dimensional array to a function. Sometimes it's 3 by 5, sometimes it's 10 by 10, sometimes it's 1000 by 1024, blah, blah, blah. What type is my A? It's a double star star. So I can just accept it as a double star star. No brackets. You can't use empty brackets. No column size because it's going to be variable. Just take it as a double star star. So my A goes in as a double star star into a function. The only thing I need to know in the function is what? You understand? I can use brackets because I just did. So this formal parameter called A, let's call it A for array, can also use brackets. But I just have to know what?
Starting element.
I need to know the number of rows and columns. So now you can pass in a two-dimensional array of arbitrary dimensions as a two-dimensional pointer, pass in the rows and the columns, have fun. It will dereference them correctly. Okay, so that's that. Okay, any questions about that? Oh, the last part here is the overloaded method, the dynamic 2D my A. So clearly, when that method is called, it's not this one because the parameters don't match. It's this one. So dynamic 2A sends in a double star star, which matches this one. Look what this thing does. It says delete the buffer star A. What's the buffer star A? So I dereference A and I delete the buffer. I am deleting that buffer. And then I'm finally deleting, no, sorry, I think now I'm getting confused, okay. So this is my A in here, it's going to be A. So yeah, it's correct. It's going to be deleting this buffer. This buffer is going to be gone. Where's it going to? Back to the heap, right? And then finally I delete star A, so I'm deleting this finally. Delete the bracket here. So delete this, delete that, and now we got our number back. Okay, any questions on that? Bad name. It should be called delete to D or something like that. Allocate to whatever. You get the idea. All right. So this is basically how to pass arrays without mapping functions, and so we already kind of talked about that. All right, briefly I want to talk about file I/O. You guys have already done some I/O in the hospital program, so you guys are familiar with that, so I'm not going to talk too much about it. I want to point a couple things out to you. One of them is some of the inheritance hierarchy of the I/O classes. The base class of most I/O stuff is from the iOS class. iOS. How many people have heard of the iOS class? Okay. iOS. Now, underneath the iOS class, we have a subclass called iStream, which is an input stream. See the arrows, the way they're going? They're wrong, right? They're going the wrong direction. Because that's a superclass. Should be going the other way. That serves me right for using somebody else's pictures. Okay, so iStream is a subclass of iOS. OStream is a subclass of iOS. IOStream is a subclass of iStream and OStream. IOStream is an input-output stream. It is both an OStream and an iStream. What is an FStream? An FStream is a file stream. What's a file stream? It is a subclass of IOStream, which means an FStream is an IOStream, is an iStream, is an OStream, and is an iOS by inheritance. And also, an FStream is not connected to output or input. It can do both because it is inheriting from IOStream. An IFStream is an input file stream. An OFStream is an output file stream. And IFStream inherits only from iStream and iOS. And OStream inherits only from OStream and iOS. And of course, iOS base. Okay, there's some other types. So there are file streams, there's S-stream, or string streams. So you can put things into a string and then use a string like a file. Okay. A couple of things I'm going to just go, so I can go quickly through this. Files. So let's say I have an input. So IFStream is input file stream, file in. Then I say file in open, file name. Now, when I do an open, that's a method from the IFStream class, right? What will fail return? What type? Let's start with that. Say it. Boolean. It's going to be a Boolean. It's going to return true or false. So that's why we're using it. It's part of conditional. It will return true or false. It will return true if there was a failure. Otherwise, it will return true. But what do we mean by what kind of failure? So whenever we do an operation on a file, if that operation is successful, we put a 0 into a bit that says, nice job. Whenever we do another operation, if we fail, we put a 1 in the little error flag location. So basically what fail does, it basically can check whether the last operation on the file object succeeded or failed. So therefore, if fail is true, that means the open failed, because that's the last thing we did. Okay? And then you can close the file, of course. So other methods that you can use are EOF, returns if end of file is reached. End of file is actually a constant. End of file is a constant. It's actually pound defined in one of the header files as a -1. Okay? Bad returns true if an invalid operation was requested. Fail if an operation has failed or bad is true. Good returns if none of the above is true. RD state returns the internal error state bit vector. This is very, very cool. So what do I mean by internal error state bit vector? So think of a file having an integer value, which we'll call it the error vector. Now, if it's an int, I don't know if it's an int or a long int, I don't know. But let's say it's an int. So let's say it says 32 bits. So basically what we have is whenever something is going on with the file, if there's an issue, we can set a bit to 1 to indicate that there's a problem here, or we can set it to 0. So this this particular error state bit vector will have a configuration. So if you want to look at the bit vector, you can basically say, okay, give me the RD state. And if you get the RD state, then you can use a mask. So let's say you want to mask out the 16th bit, because that's important to you. So you take the RD state, you take this one, you take 0 followed by everything is 0 and a 1, and you shift it 15 times. And then you do a bitwise AND. And you find out if that's non-zero. If it's non-zero, you got a 1 set in that location on the RD state. Does that make sense? So this gives you indication of all the different errors or issues that a stream can have. Now, clear in state is overloaded. If you clear with no parameters, it will set the error state bit vector, everything's fine again. Okay? If you say clear and then you give it a specific value, it will set the error state to whatever value you give it. So again, so be careful because you can really mess up stuff. So this is powerful stuff. You don't necessarily want to do that. Okay. So cout, you guys are familiar with the cout object. So we can do character output. Cout has a method called put. And if you put a character ch, that's going to basically do what? It's going to set the character out to the standard output stream. Get. If you do a get from here, it's going to basically, it takes the parameter by reference so that it can change the parameter by setting it equal to the value in the input buffer that's the next character. Okay? Note that get returns an int value, so cin.get. So cin.get is going to return an integer, but that integer really will be a character. So why is it returning an integer? Anybody know? What's the smallest value for a character in terms of ASCII? 0. What's the biggest in ASCII? 255. Now, if you use Unicode, then you have 0 to 64k minus 1. Fine. But what I'm saying here is that the values for the smallest value for a character is 0. The biggest value is the biggest value you can have. So if you have an 8-bit char, it's 0 to 255. That's it. But it returns an int. So that means it always returns an int. And the reason it does that is because we always want to check when we're reading, especially from a stream or from a file, that we didn't get past the end of file. And the end of file marker is -1. There is no -1 character. So if you try to get a character and you get a -1, that means you tried to read the end of file, which means that you read the end of file, the RD state is going to get set, that you've reached the end of file or that you had a bad read. So in this case, we can check while c equals cin.get not equal to -1 or not equal to EOF. Continue. Because if it's equal to EOF, you just read the end of file marker. So when you go past the end of file, you get an end of file marker, and that's on -1. And you know what that looks like? It's going to have all 1s. So if you have an int with 32 bits, end of file is going to look like 32 1s. But every other character that's not end of file is going to have 24 zeros, and then any combinations of 0s and 1s in that last byte. So to get the -1, we need to have some more available stuff, because basically if you have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 8 of them, that's a 255, that's a character. So if you get 24 zeros and 8 1s, that's a character. But if you get 32 1s, that's end of file. GetLine is a cool method. Basically what you do is you will give it a buffer. So if you have a buffer, if you allocate an array of 10,000, you can say cin.getLine buff, and then you give it a value. And if you have that, it will put up to n-1 bytes to the delimiter, or end of file adds a null character. Okay? And then gcount returns the number of bytes on the last get line. So this is like the get line count, gcount. Okay. Now, I want to talk about binary I/O, because binary I/O is very powerful, and all modern languages have it. Java, C#, C++ has it. Who can tell me what is binary I/O? Some of you, I have some undergraduate students here, right? Did you guys have me for anything like, you took file structures, so you did a lot of binary I/O. How many of you are familiar with binary I/O? Oh, please, don't tell me you're the only guy. You don't know binary I/O?
I took Java 1 and 2, so it's about.
You took Java with me?
No, I took it with Sabrina.
Oh, so you know, okay, that's fine, but that's the intro Java. That's fine, that's good. Okay, so let me talk about binary I/O. Okay, Chris, you want to tell us what is binary I/O? Does not want to say what's binary I/O. Okay, put him on the spot. Okay, so basically, a file. There are two types of files. There are text files, and there are binary files. What's the difference between a text file and a binary file? Well, think of it this way. Think of your screen. Let's say I have a code in C++ that says cout, output operator 6. Okay? What are you going to see on the screen? 6. But when you see it, if you could peer into the memory location, if you say cout n, and n is 6, there's an n, has an address, there's 32 bits in there, there's 24 zeros, and then 0, 0, 0, 0, 0, 1, 0, 1. 0, 0, 1, 1, 0. Whew. Okay, that's a 6. So therefore, when you say cout n, and n is 6, and you get a 6, that's not what was in the memory. That's called a conversion. That bit pattern of 24 zeros, and then 0, 0, 0, 0, 0, 1, 1, 0, has to be converted to a 6. And of course, if you say iOS hex, it might have to be converted to a hexadecimal number too, but that's a different story. But the default conversion is int. If you say cin into n, and you type in a 6, that 6 doesn't go into the memory location. It has to be converted to 0, 24 zeros, 0, 0, 0, 0, 0, 1, 1, 0. That's a conversion. Well, what do you think? What do you think is the cost of conversion in terms of programming? It's time, right? Conversion is not instantaneous. Watch this. Let's say we have a cin into n, and you type in minus 1, 2, 3, 4, 5. Now, when you're typing in minus 1, 2, 3, 4, 5, you are not typing a number. You're typing characters. You're typing the minus character. You're typing the 1, which happens to be ASCII 49, ASCII 50, ASCII 51, 52, and 53. That just happens to be the ASCII values. And literally, when you type those characters, you get those numbers in the input buffer. So when the overloaded input operator into an int from iStream is reading that bunch of text, it looks at the first character, says, are you a digit? No, that's a minus sign. Oh, well, that's okay. You can have a minus sign to begin with. I'm going to let it go. I'm going to remember that because I'll have to negate whatever you give me. Not in a bad way. You just have to negate it. So now it goes to the next character and has to test that this character is a digit. If it's another minus, it's going to say, I'm sorry, you got one of those. That's it. It's no good. That's called parsing. It's called conversion. So it finds that 1. But how does it know it's a 1? It knows because the value of that 1, which I told you is 49, is greater than or equal to the ASCII value of 0, which is 48, and less than or equal to the ASCII value of 9. Because that condition is true, that 1 is said, you're a digit. But now it has to say, well, what the heck are you? So it does, it takes the ASCII value of that approved digit and subtracts it from the ASCII value of 0. So it does 49 minus 48 and comes up with 1. Then it goes to the next element in the buffer. That's a 2. It has to find out if a 2 is a digit. So it sees if the ASCII value of the 2 is greater than or equal to 48 and less than or equal to the ASCII value of the 9. Yes. In that case, what I'm going to do is the value that I'm converting, I'm going to multiply that 1 by 10, and I'm making a 10, and then I'm going to add to it the ASCII value of the 2 minus the ASCII value of 0, giving you a 12. You follow what I'm doing? Then it's going to shift that for the next digit, going to shift that, multiply that by 10 to get a 120, and then add the difference between the digit 3 and the character 0. 123, 1234, 12,345. Then it comes to a delimiter. It says, you're a delimiter. I'm done. And no problems. Oh, but wait a second. You gave me that minus sign. Bummer. Bummer. So what I have to do is, so now, as it's converting it from the input, it now has 32 bits, which are equal to 12,345. But now it's negative. So now it has to do a 2's complement on it. So it basically flips all the bits, and then it issues a +1 operation on the ALU. After all that's said and done, it takes that 32 bits, puts it into the location where n is stored. And that's the story of the input conversion. I'm not even going to get into the output conversion right now. You can imagine it's pretty much the same. Okay, that's called conversion I/O, and all text files are read and written exactly like that. Here's how binary I/O works. Okay, so let's say I have a file. Let's say I have a file, and the file contains binary integer values. What does that mean? It means that the file is filled with a continuous 4 bytes of zeros and ones, where each 4-byte sequence represents an int. So if this file has 4,000 bytes, exactly 4,000 bytes, then there are exactly 1,000 ints in there, because each of them is going to be 4 bytes. So therefore, what I can do is, if I have this file, I can simply say, read this file and give me 4 bytes. You know what it does? It goes to the file, grabs 4 bytes, puts them into the address. Done. Done. But what? Done. It's finished. It just takes those 4 bytes from the file, moves them into the memory of that variable. Give me the next one. Read next 4 bytes. So that's what binary I/O is. The problem with binary I/O, if you look at that 4,000 byte binary program, it's going to look like a bunch of crazy characters. You've seen those before. Those are binary files. Either that or corrupted files. Can't tell the difference, really. So that's the idea. So to read binary, now I'm using cin, but we can also use fin, like file input stream, fout, file output stream. So cin, typically cin doesn't, reads from standard input, but as I will show you, you can also redirect your cin to go to a file. That can be done on a command line very easily. It's called file redirection. So you can have cin go to a file. So it doesn't stop for you at all, but don't worry about that. The idea is that what I'm saying, the read method is a binary read. It says, go to this stream. And what I want you to do, I want you to take this many bytes from this stream and put them into this address. It's just reads, writes. There's no conversion, there's no checking. Every 4 bytes is an int. Fine. Now, in this case, I'm reading a buffer of chars. But this could be, the buff could be a int pointer buff. Okay? So that's the read. Let's look at the write. So the write would be, you go to an output stream and you say write. So read is binary input, binary output. What you're doing is, I want you to go to this stream and write this many bytes starting at this address. That's it. And it just, so for example, so if you put 1,000,000 in here in this parameter, it's going to take 1,000,000 characters and just dump them into that stream. So reading an array of rational objects. We've seen the rational class. So for example, so here is my array is an array of rationals, which I initialize to a couple of rational objects, 2/3 and 3/7. Then I create an OF stream, an output file stream. This is the object. The constructor takes the name of the disk file, and then I'm using the iOS superclass enumeration called out. What's the value? I don't know. I don't care. As long as I do that, then I'm telling the C++ system that I'm creating an output stream, output file, and then I simply go to this output stream and I use a binary write, and then I say size of rational, well, see this is my array, it should be my array. Sorry about that. So what is the size of my array? I don't know, but I do know that it's in this scope, so therefore whatever object size this is and this is, size of this array is going to be the number of bytes that are in this entire set of array of 2 rational objects. And then I want you to write it from this address, which is my array. So go to this address and dump this many bytes into this stream. That's it. And this is reading. So suppose I have a file where I wrote rationals this way. So now I have a rational array of 2 rational objects possible. And I create an input file stream in, same file, but this time I open the file for iOS in. And I simply go to this input stream and I read 2 times size of rational. What size of rational? I don't know. Size of rational. It's going to have all the size, how many bytes that object takes. So that many bytes, and I want you to read them into this address. Notice that the address is being cast as an unsigned char star. And when you're writing it out, you cast this, which is of type rational pointer, to an unsigned char pointer. And the reason for that is because the write method is writing bytes. So you give it a byte pointer, and you give it the number of bytes you want to write, or the number of bytes you want to read. So even though my array is what? Is a pointer to rational, I'm casting it as an unsigned char pointer, because this function read is very simple. It just wants to move characters from place to place. So it expects pointers to be pointers to character buffers, and it takes this number as the number of characters to copy. Okay, I think we're running a little time. Let me just double check. How's everybody doing on the program? Did you guys get my program to run? You better. Aladdin? Do I have to dispatch Aladdin on you guys?
It looks good.
Everything's happening good?
Yeah, check it
Okay, all right. So I'm going to stop here.